Hello everyone, myself Samit Kumar, lecturer of Mechanical Energy Engineering Department, IIMT College of Polytechnic, Greater Noida. So I will discuss about overview of air conditioning system. So here we can see that air conditioning system. Now here there is a three components. One is a condenser, another is a evaporator, and third is a compressor. The whole three components work with each other with the complete complete cycle. Then we will obtain a desired temperature. So here we can see that the pipe diagram of air conditioning system. Now here we can discuss about the refrigerator. Refrigerator is work in a cycle to convert one phase to another phase. So here refrigerator there are four components. One is the evaporator, another is a compressor, and condenser and expansion valve. Here first of all we will give the sub input in a compressor. Here a complete refrigerant in a vapor form. It will convert it after compression. It will goes to the condenser with the high pressure and high temperature, and after that it will goes to condenser is nothing but it will work to release the heat to the surrounding, and the very warm air is heated, that is goes to the surrounding. Now after that it will goes to expansion valve. Here is completely convert into vapor form to liquid form. After that its temperature goes down and down up to minus 25 degree centigrade, and temperature is minus 25 degree grade, and pressure is also decreases 800 kilopascal to the 120 kilopascal. After that complete converted at low temperature water vapor of refrigerant is goes to evaporator. Here we will use to room air, that is heated room air is goes to the evaporator, and refrigerant is converted into the steam from the liquid phase, and this cycle is complete continuously work. That's why we will convert into the hotter air to the colder air. So next, how to check the performance of the refrigerator and air conditioning system. There is the COP of refrigerator, that is the coefficient of performance, and here we can see that from the diagram. Here complete cycle of the refrigerator, and given to some input in terms of work, and this work is done by the compressor. After that it goes to condenser and it will after that goes to expansion valve, except after that it will go to evaporator. This cycle is continuously work, and we will desired output is lower temperature. In air conditioning system we want low temperature of the surrounding and room, that is the lower temperature, and rest hotter temperature as goes to the surrounding, that is a warm environment. So this is the equation. COP of refrigerator is desired output upon required input. Desired output is lower temperature, lower heat, that is Q lower upon work input, that is the work input is the work done by the compression, that is also written in this form. The lower heat upon higher heat per minus lower heat. When decrease the lower temperature, so refrigerator COP is also decreases, that is directly proportional to the lower temperature of the COP of refrigerator. So next things is the heat pump. Heat pump is nothing but it is similar to the refrigerator process, but here is a required output is hot temperature inside a space, inside the room, inside the space. So here outer temperature is hot air. So here two example, one is the domestic room heater and another is air conditioner. They are also convert the lower temperature to higher temperature with the help of heat pump. After that, so I will discuss about the performance of the heat pump, how to calculate. So same procedure will be there, but here is required desired output is higher temperature, higher heat. So there is same process is done by the system, but this what here is required things is a warm environment. In winter season we want warm environment, in a summer season we want cold environment. So heat pump is used in a winter almost, and we can retain in this equation COP of heat pump is desired output upon required input. Here desired output is a higher temperature, that is a higher temperature of the space. So we can retain as heat higher heat upon work input, that is also written as a higher heat upon higher heat minus lower heat, that is directly proportional to the heat. If lower temperature is decreases, that means COP of heat pump is increases. After doing some calculation we will get the COP of heat pump is equals to COP of refrigerant plus 1, that means greater than COP of heat pump is always greater than COP of refrigerant. Now we will obtain from some conclusion with who is better use for space hot space will required in a space is hotter. One is heat pump, another is electric heater. So both will be heat the environment from the using of two systems. But we can use electric heater. So if work is consumed by the electricity resistance heater, then heat released to the space will be almost equal to the work. But if this energy is utilized in the heat pump, then the heat pumped to the space will be, it means the equation is shows the work is consumed by the electric heater is same amount of heat is released, but here heat pump we will take in some work input, it will give the heat is greater more than electric heater. So the better use of heat pump as compared to electric heater for uh, general use. So I will discuss about next is Carnot refrigeration cycle. This is the maximum output COP performance of the Carnot cycle, where we can see that the TS diagram of the Carnot cycle. Here is the phase diagram. Phase diagram, that is converted into liquid to vapor, liquid to vapor, a vapor to steam. That is wetted region. Here we can see that a whole process is done in the wetted region of the Carnot cycle. It will give the 100% COP. That is not possible in real life, but uh, hypothetical cycle we will conclusion from this cycle the COP heat is released by the system, that is optimum COP. So uh, whole first is 1 to 2 is the work done by the compressor. After that 2 to 3 is the condenser process, condenser process, and after that 3 to 4 is expansion valve installed, and 4 to 1 is evaporator. That is a whole equipments are work one by one, and it will complete the cycle and give the desired temperature from the Carnot cycle, refrigeration cycle. So now taking into some few example of the Carnot refrigeration cycle, consider the air conditioning, which refrigeration effect is 5 degree, and the reject the heat to the surrounding is 30 degree. After the calculation of COP of the Carnot, we will get the 11.12. It means we can conclusion we can goes to the conclusion is 100 kilowatt of power is consumed, then it will give the 1112 watt. That is work COP work by the condenser system. After that, given another example, here 2 kilowatt is input supply to the condenser refrigeration system. It will give the output COP is 1.5 torr refrigerant. That is, in terms of kilowatt, is 5.27. So after that, the next example is the considering 75% of running time of the cycle, then power consumed is equals to 1.5 kilowatt. That is after we will get from the experiment. And now we will conclusion comes to the conclusion is if the COP decreases, the more responsible to consumption of power is increases. That means if that means the temperature of the lower temperature is goes to decreases, the refrigeration temperature goes to decreases. That means COP of refrigeration system is also decreases. That we can also see in a previous equation. There is a directly relation between the COP and lower heat temperature. Now we will discuss about the refrigerator reverse Carnot cycle. Reverse Carnot cycle and comparison between the reverse Rankine cycle and Carnot cycle. We will also discuss about it. Now we are discuss about the reverse Rankine cycle. Here, nothing will. This is whole process is similar like that Carnot cycle. What here is change is expansion takes place in throttling device. Here in a Carnot cycle, we can see that the expansor valve we are using a process 3 to 4, but here we can see that in terms of expansion valve we can use throttling valve 3 to 4 process. So we are using the throttling device to improve the system COP of system. That's why we are using the expansion valve to the throttling valve. So after that, we can see that MTS curve. Here is the curve of reverse Rankine cycle. Here 3 to 4 we can see that in Rankine Carnot cycle, that is the vertical entropy is constant, entropy is constant. But here in Rankine cycle, we can see that the 3 to 4 process is constant enthalpy process because of throttling. We are using the throttling valve. Here throttling valve is doing that is a pressure and temperature both will be decreases simultaneously and improve the performance of the system and cycle. So here condenser, here we can also see that 2 to 3 is a takes a place in a condenser that is at a constant pressure curve. The complete condenser process is done at the constant pressure. So next I will see that the comparison between Carnot cycle and Rankine cycle. So we can see that from the curve 1, 2, 3, 4 dash, that is a Carnot cycle curve, and 1, 2, 3, 4 is the reverse Rankine cycle curve, and hedged area, that is the hedged area, it final output of the Rankine cycle, and a complete 4 dash to 1 is area, hedged area is Carnot cycle output area. That is the comparison. The both these the reversible cycle. But here we are see in the reverse Rankine cycle, the area is less as compared to Carnot cycle. The rest small area is 4 dash 4 and CD. This area is also told as throttling loss. That is the throttling loss in the Carnot cycle. This loss is considered in a Carnot cycle. That this is the comparison of the two cycles we are obtaining, and we how to calculate the refrigeration effect, refrigeration capacity effect is similar things. Here we are calculating refrigeration capacity. It means heat is equals to out outer sorry input heat is equals to refrigeration mass rate into enthalpy of 1 minus enthalpy of process number point 4, that is give the refrigeration capacity. That is the refrigeration capacity is the final output is given by the system, that is the q heat exerted by the system, that is the refrigeration capacity. And here here m dot r is the mass flow rate of the refrigerant, and h1 minus h4 is known as the specific refrigeration effect. Now we will comparison with the Carnot cycle and condenser. Then heat rejection in case of the Rankine cycle increases is comparison to the Carnot cycle. Here we can see that heat rejection. Where is the heat rejection? Heat rejection in process 2 to 4, 2 to 3. Now we will see in the Carnot cycle where heat rejection is less, but here the Rankine cycle we can see that the max A1 area is extra, that is the maximum heat rejection from this cycle. So we can say that the efficient, more capable, more efficient, more capacity performance by the Rankine cycle as compared to Carnot cycle, because input is same, input which also increases in Rankine cycle as compared to Carnot cycle, but rejection is a more heat from the system, that is the more this is more desirable for uh, refrigeration system. So we can use the reverse Rankine cycle as compared to Carnot cycle. H2 minus H1 is known as specific work of the compression. H2 minus H1, that is the enthalpy of point 1 to the enthalpy of point process point 2, that is the difference of the enthalpy of 2 minus enthalpy of 1, that is the specific work compression, or simply the work of compression. Okay, next we can see that here heat Carnot his area under the curve E dot E 2 2 dash 3 C and E, that is the complete area of the Carnot cycle. Now Rankine cycle is E 2 2 dash 3 4 and D, that is the complete hedged area is the Rankine cycle. So that is the we can say that 2 dash 2 and 2 dash 2 and 2 dash is known as the superheated horn, that is the high temperature maintained at that particular area of the refrigerant in a vapor form for better performance of the system. So calculation of the reverse Rankine cycle, how to calculate the COP of the reverse Rankine cycle is a similar about previous. We can also see that the higher heat desired output upon work input. The desired output is process number 4 to 1, that is minus H1 minus H4, higher enthalpy minus lower enthalpy. So H1 minus H4, that is the desired heat from the evaporation process, and work input by the compressor, that is the H2 minus H1. This is the ratio will give the COP of reverse Rankine cycle. The mass flow rate of the system can be written as mass flow rate of system, also written as the volumetric flow rate and the specific volume, that is volumetric flow rate upon specific volume. So let us assume that the thermal efficiency of heat engine, that is 0.3. Now we will see written as the work done upon higher heat supply, that is the efficiency 30%. And we will calculate reverse Carnot cycle, and heat pump is also we will calculate the heat pump, uh, that is inversely proportional to the efficiency of the efficiency of the heat engine to the heat pump of COP. And COP of the refrigerant, the inversely proportional of the efficiency of the heat pump. And now calculate after that COP of heat pump is equals to also seen that COP of refrigerant plus 1. After that we will calculate from the refrigeration COP of refrigeration system, that is 2.33. If the thermal efficiency of the heat engine is 30%, then after the calculation by using the heat pump relations with the refrigeration COP of the refrigeration, that is COP of heat pump plus minus COP of refrigerant, that is equals to 1. And after the calculation we will get the 2.33. So we can study about deeply study about the complete refrigeration air system, how to work and how to operate, and how to obtain the desired temperature of the space. And I hope you are learn from this session. So thank you to all for watch my video.